That fuzzy patch of light you can see with your naked eye on a clear night isn't a star. It's an entire galaxy containing 1 trillion suns, and it's so far away that the light reaching your eyes right now left before modern humans existed. The distance to Andromeda isn't just big. It's the kind of distance that breaks our ability to understand what distance even means. Stand outside tonight and look up. Find that dim smudge in the constellation Andromeda. You're looking at photons that traveled for 2.5 million years to reach you. When that light began its journey, our ancestors were Homo habilis, barely recognizable as human, chipping away at primitive stone tools on the African savanna. They couldn't speak, couldn't write, couldn't conceive of galaxies or light years, or the vast cosmic oceans separating us from that distant island of stars. 2.5 million light years. Let's start there, because that number is where our intuition goes to die. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. A light year measures how far light travels in 1 year. Light moves at exactly 299,792,458 meters per second. Fast enough to circle Earth 7.5 times in a single second. Fast enough to reach the moon in just over a second. This isn't just fast by human standards. It's the absolute speed limit of the universe itself, the maximum rate at which anything, information, causality, can propagate through space. 1 light year equals 5.88 trillion miles. Not billion, trillion. Andromeda sits 2.5 million of those years away. Multiply it out, and you're looking at 14.7 million trillion miles. Your brain can't hold that. Mine can't either. We evolved to understand the distance between trees, between hunting grounds, between villages. We can grasp a mile, maybe 1,000 miles. We can stretch our minds to comprehend the 93 million miles to the sun if we really try. But this is different. Here's what makes it worse. Even traveling at light speed, which nothing with mass can actually do, the journey would take 2.5 million years. Build a perfect spacecraft that somehow breaks every law of physics we know. Accelerate to 186,282 miles per second, and you'd still need to maintain that impossible velocity for longer than anatomically modern humans have existed. Let's bring this down to Earth for a moment, because the abstract numbers don't capture the real horror of it. The Parker Solar Probe is the fastest thing humanity has ever built. In December 2024, it reached 430,000 miles per hour as it screamed past the sun. That's 119 miles every single second. At that speed, you could travel from New York to Los Angeles in less than half a minute. It's still nowhere near fast enough. At Parker's record-breaking velocity, reaching Andromeda would take 3.9 billion years. Not million, billion. The Earth itself is only 4.5 billion years old. The journey would outlast the entire history of complex life on our planet. Every dinosaur that ever lived, every mammal, every human civilization that has risen and fallen, all of it would fit comfortably into the time it would take that spacecraft to arrive. Want something more relatable? Hop in a Bugatti Veyron, the fastest production car ever made. Top speed of 270 miles per hour. The trip would take 2.54 million years, assuming you could somehow drive through the vacuum of space and never stopped for gas. Even Voyager 1, currently humanity's most distant ambassador, crawling away from the Sun at 38,600 miles per hour, would need longer than the current age of the universe to reach Andromeda's outer edges. The math is brutal no matter how you calculate it. But here's what really twists the knife. Andromeda is our closest major galactic neighbor. In cosmic terms, it's right next door. We're practically roommates. The observable universe stretches 46.5 billion light-years in every direction. Galaxies exist so far away that we see them as they were when the universe was young, when the first stars were just beginning to forge heavy elements in their cores. Some galaxies are receding from us so fast that their light will never reach Earth, carried away by the expansion of space itself. Compared to those incomprehensible distances, Andromeda is close, intimate even, and we still can't reach it. You might be wondering why we're talking about distance in years instead of miles. Why complicate things with this light-year measurement? The reason cuts to the heart of what makes cosmic distances so profoundly strange. When we measure earthly distances, we're measuring space. How much ground sits between point A and point B? But in astronomy, we're measuring something else entirely. We're measuring time. Look at Andromeda tonight, and you're not seeing the galaxy as it is. You're seeing it as it was 2.5 million years ago, frozen in time by the speed limit of light. The galaxy could have changed dramatically since then. Stars have been born and died. Supernovae have exploded. Planets have formed around young suns. If intelligent civilizations exist there, they could have risen, flourished, and fallen to dust, all without our knowledge. We won't know about any of it for another 2.5 million years. This temporal disconnect gets even stranger when you consider that Andromeda, unlike most galaxies, isn't moving away from us. It's approaching. Most galaxies are receding, carried by the expansion of space like raisins in rising bread dough. The farther away they are, the faster they flee. But Andromeda is racing toward us at roughly 68 miles per second, pulled by the mutual gravitational attraction between our two galaxies. In about 4.5 billion years, current models suggest we might collide. Though recent data from the Gaia spacecraft has thrown doubt on this prediction, showing only a 50% chance of a head-on merger within the next 10 billion years. When you factor in gravitational influences from the Large Magellanic Cloud and Triangulum Galaxy, the odds of collision within the next 4 to 5 billion years drop to just 2%. But here's the thing. Even if we do collide, even if our two galaxies merge in a slow-motion cosmic dance lasting hundreds of millions of years, the individual stars won't actually hit each other. Space between stars is so vast that they'll pass like ghosts through each other's formations, rearranging themselves into new configurations without ever touching. That's how empty space really is. Andromeda contains roughly 1 trillion stars. The Milky Way holds somewhere between 200 and 400 billion. Pack all those stars together, and there's still so much emptiness between them that a collision of galaxies doesn't mean a collision of stars. The scale defies comprehension in every direction you look. Let's try another angle. Shrink the universe down to something manageable. If the sun were the size of a basketball, Earth would be a small bead about 26 meters away. The moon would orbit that bead at roughly 65 centimeters. On this scale, how far away would Andromeda be? still billions of miles. The model breaks down because no matter how much you shrink things, the ratios remain absurd. The distances between galaxies dwarf the distances between stars, which dwarf the distances between planets, which dwarf the distances between moons. We're trying to grasp something that exists on a scale our minds never evolved to process. Here's another way to think about it. If you could travel at the speed of a commercial airliner, cruising along at 500 miles per hour, the journey to Andromeda would take 570 billion years. That's more than 40 times the current age of the universe. You could make the trip to the moon and back 50 times for every single mile you'd need to travel to reach Andromeda. You could circumnavigate Earth 963 times and still not have covered the equivalent distance. The numbers stop meaning anything after a while. They become pure abstraction, symbols on a page that point towards something our brains simply cannot hold. But Andromeda isn't an abstraction. It's real. Right now, as you read this, 1 trillion stars are burning in that galaxy. Planets orbit those stars. Physics operates there exactly as it does here. Time flows forward. Gravity pulls. Light propagates at exactly 299,792,458 meters per second, and it's all happening 2.5 million years ago from our perspective, locked behind an insurmountable barrier of space and time. This is what astronomers mean when they talk about look-back time. The past isn't really past out there. It's ongoing, present, immediate. The light from Andromeda that's reaching Earth right now is genuinely old light, ancient photons that have been traveling since before our species existed. When you observe distant objects, you're not looking at where they are. You're looking at where they were. The universe becomes a time machine pointed backward, and the farther you look, the deeper into history you peer. The most distant galaxies we can observe exist so far away that we see them as they were just a few 100 million years after the Big Bang, when the universe was young and strange, still cooling from its violent birth. Those galaxies might not even exist anymore in their current form. They've had nearly 14 billion years to evolve, merge, transform. We'll never know what they look like now. The information simply can't reach us yet. Andromeda, at 2.5 million light-years, is close enough that the look-back time feels almost reasonable. 2.5 million years is nothing compared to billions, but it's still longer than our entire existence as a species. Imagine trying to communicate with someone in Andromeda. Send a radio message today, traveling at light speed, and it arrives in 2.5 million years. If they immediately respond, you get their answer 5 million years from now. The round-trip communication time exceeds the entire span of human history by orders of magnitude. It exceeds the lifespan of civilizations. It exceeds the stability of continents, the persistence of languages, the survival of species. Any conversation becomes impossible not because of technological limitations, but because of time itself. This is the prison that distance creates, not just spatial separation but temporal isolation. The universe has built-in lag time, and at cosmic scales, that lag becomes unbridgeable. Yet despite all this, despite the crushing impossibility of the distance, Andromeda remains visible to your naked eye. On a moonless night, far from city lights, you can see it without any equipment at all. A faint smudge against the darkness. 3 times the apparent width of the moon, though so dim that your eye can barely register it. That visibility is almost offensive, given what we now know about the distance involved. It seems wrong that something so impossibly far away should be visible at all. The light has traveled for millions of years through the void, spreading and weakening, and yet enough photons still arrive at Earth to trigger cells in your retina. Ancient astronomers noticed it too, long before they understood what they were seeing. In 964 CE, the Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars as a nebulous smear, a small cloud among the stars. That was the first written reference to Andromeda, though people had surely noticed it before. You can't miss it once you know where to look. For centuries, astronomers argued about what it was: a nebula within our own stellar system, a cloud of glowing gas, some strange atmospheric phenomenon. The answer came in 1925 when Edwin Hubble identified Cepheid variable stars within Andromeda. These stars pulse at predictable intervals, and their brightness correlates directly with their pulsation period. By measuring how bright they appeared versus how bright they actually were, Hubble calculated their distance. The result shocked the astronomical community. Andromeda wasn't part of the Milky Way. It was an entirely separate galaxy, an island universe comparable in size to our own, sitting at a distance that staggered the imagination. That discovery fundamentally changed our understanding of the cosmos. The universe suddenly became vastly larger than anyone had conceived. We weren't alone in a single galaxy. We were one galaxy among countless others, separated by distances that made even the vast expanse of the Milky Way seem trivial. And Andromeda was the closest one we could study in detail. That closeness, that accessibility, makes the impossible distance somehow worse. If we can see it, if we can photograph it, if we can resolve individual stars within it using powerful telescopes, then surely we should be able to reach it. But we can't. The gap between what we can observe and what we can touch has never been wider than it is when we look at Andromeda. And this gap, this cosmic moat protecting one island universe from another, is what we need to truly understand if we want to grasp our place in the universe. The scale of the distance only becomes real when you try to build something that could cross it. Let's start with the fastest object humans have ever created. The Parker Solar Probe, launched in 2018, holds the speed record. At its closest approach to the Sun in December 2024, it reached 430,000 miles per hour. That's 692,000 kilometers per hour. That's 0.064% the speed of light. At that velocity, traveling to Andromeda would take 3.9 billion years. That's not a typo. 3.9 billion years. For context, Earth itself is only 4.5 billion years old. Complex life didn't appear on our planet until about 600 million years ago. Humans have existed for roughly 300,000 years. Civilization for maybe 10,000. The Parker Solar Probe would need to travel for longer than multicellular life has existed on Earth to reach Andromeda. And that's our fastest spacecraft. Optimized for velocity, stripped of everything except what's necessary to survive the Sun's corona. What about Voyager 1? The spacecraft that's traveled farther from Earth than any other human-made object. It's currently moving at 38,600 miles per hour, respectable by terrestrial standards, pathetically slow by cosmic ones. Voyager 1 would take approximately 44 billion years to reach Andromeda. The universe itself is only 13.8 billion years old. Voyager would need more than 3 times the current age of the cosmos to make the journey. And these are our success stories. These are the spacecraft we're proud of. Now imagine we had unlimited funding and political will. Imagine we dedicated the entire global economy to building the fastest possible spacecraft using current physics. Chemical rockets won't cut it. The tyranny of the rocket equation makes interstellar travel with chemical propulsion essentially impossible. You'd need more fuel than exists in the solar system. Nuclear propulsion offers better prospects. Fusion rockets, if we ever perfect them, could theoretically reach 10% the speed of light. That would be revolutionary for interstellar travel. At 10% light speed, reaching Andromeda would only take 25 million years. Only. 25 million years is 5 times longer than the entire genus Homo has existed. It's longer than the time since the extinction of the dinosaurs. The continents would drift to different positions. New mountain ranges would rise and erode away. Entire ice ages would come and go. But let's push further into speculation. What if we could somehow reach 90% the speed of light? Setting aside the tremendous engineering challenges, the energy requirements, the problem of interstellar dust impacts at relativistic speeds. Just imagine we solved all of that. The journey would take 2.7 million years. Still longer than modern humans have existed. Still an incomprehensible span of time. But at least we're getting somewhere, right? At least the numbers are starting to approach something vaguely conceivable, except there's a problem. Time dilation. Einstein's special relativity tells us that as you approach light speed, time slows down for you relative to the outside universe. At 90% light speed, time would pass about 2.3 times slower for the travelers than for people back on Earth. So while the journey would still take 2.7 million years from Earth's perspective, the travelers would experience only about 1.2 million years. That's still absurdly long, but it introduces something even more disturbing than the journey time itself. The disconnect between traveler time and Earth time means that by the time you arrived, Earth would have aged far beyond your experience. Any communication with home would be separated by millions of years. You'd be culturally, evolutionarily, temporally severed from your origin. And we're still talking about reaching 90% light speed, which is pure fantasy with current physics. The energy requirements alone are staggering. To accelerate 1 kilogram of matter to 90% light speed requires about 2.5 times 10 to the 17th joules. That's roughly the total energy consumption of the United States for an entire day. For 1 kilogram. A modest spacecraft might mass 1,000 kilograms. You'd need energy equivalent to decades of global power consumption just to reach velocity. And then you'd need to decelerate at the destination, doubling the energy requirement. What about generation ships? The concept has captivated science fiction for decades. Build a massive spacecraft, essentially a mobile world, and let it travel for generations. The crew that arrives would be descendants of those who departed, a floating civilization spanning the void. For nearby stars, generation ships remain at least theoretically possible. A journey to Proxima Centauri, our nearest stellar neighbor at 4.2 light-years, might take centuries with realistic propulsion. Long, but conceivable. Multiple human generations, but not geological time. For Andromeda, forget it. Even at 10% light speed, remember, that's already wildly optimistic. The journey takes 25 million years. That's not generations. That's not even millennia. That's deep evolutionary time. The humans who arrived wouldn't be human, not in any sense we'd recognize. 25 million years of evolution in an enclosed environment would produce something entirely different. The original mission parameters would be meaningless. The culture would have transformed beyond recognition thousands of times over. The language would be unrecognizable. The biology would have shifted. You wouldn't be sending humans to Andromeda. You'd be sending the raw material that might eventually evolve into something else entirely. Something that had no memory of Earth, no connection to the mission's original purpose, no concept of why their ancestors climbed aboard this metal container drifting through the void. The psychological implications alone are staggering. How do you maintain purpose across 1,000,000 years? How do you preserve knowledge when the destination is thousands of generations away? How do you prevent social collapse when everyone aboard knows they'll die long before arrival, as will their children, grandchildren, and descendants for hundreds of thousands of generations? You can't. The concept doesn't just strain credibility, it breaks against the rock of deep time and shatters. So what about the really exotic proposals? The science fiction solutions that might actually work if physics cooperates? Warp drives. The Alcubierre metric showed that compressing space-time in front of a spacecraft while expanding it behind was mathematically consistent with general relativity. You're not moving faster than light. You're surfing a wave of space-time itself, and the wave can travel as fast as you want. There are just a few problems. The energy requirements are astronomical. Early calculations suggested you'd need more energy than exists in the observable universe. Later refinements brought that down to merely the mass-energy equivalent of Jupiter, still wildly impractical. Then there's the causality problem. Faster than light travel, even via warped space-time, potentially allows you to arrive before you left from certain reference frames. That creates temporal paradoxes that physics really doesn't like. And the engineering challenges are absurd. You'd need exotic matter with negative mass energy. We've never observed such matter. It might not exist. If it does exist, we have no idea how to create it or manipulate it. We're talking about technology so far beyond our current capabilities that the gap between us and it is larger than the gap between bacteria and spaceflight. Wormholes, same problems, theoretically possible in general relativity, practically impossible with known physics. You'd need exotic matter to stabilize them. You'd need to create or find them. You'd need to expand them to useful sizes. You'd need to ensure they don't collapse or evaporate. You'd need to survive the tidal forces near the throat. And even if you solved all of that, you still don't get to choose where the wormhole goes. You'd need to find or create one that happens to connect our region of space with Andromeda. The odds of that occurring naturally are essentially zero. Creating one would require technology indistinguishable from magic. Every theoretical solution to the distance problem requires either infinite time or impossible physics. Which brings us back to the fundamental reality. The distance to Andromeda isn't just far, it's insurmountable. Not because we lack the will or the resources, though we certainly lack both, but because the universe itself has structured space and time in a way that makes such distances uncrossable by any physical means we can currently conceive. Light can make the journey because photons don't experience time. From a photon's perspective, if such a perspective existed, The journey is instantaneous, emitted from a star in Andromeda, absorbed by your retina. No time passes for the photon. It exists in a timeless state, connecting emission and absorption in a single eternal moment. But anything with mass experiences time. Anything with mass ages during the journey. Anything with mass requires energy to accelerate and fuel to maintain life support. Anything with mass faces the grinding reality that crossing 2.5 million light-years takes millions of years at minimum, and more likely billions with realistic technology. The numbers don't get better the more you examine them, they get worse. Every realistic calculation points to the same conclusion. Andromeda is visible but unreachable, observable but untouchable. We can see it, we can photograph it, we can analyze its spectrum and determine its composition. We can count its stars and map its structure, but we cannot go there, not in any time frame that has meaning for human civilization. Not with any technology that seems remotely plausible. The distance is too vast and time is too linear and physics is too restrictive. And this is our nearest large galactic neighbor, the closest island universe to our own. If we can't reach Andromeda, we certainly can't reach anything farther. The billions of other galaxies scattered through the cosmos might as well exist in separate universes entirely. They're visible to our telescopes, but forever beyond our grasp. That's what makes the distance terrifying. Not just its magnitude, but its implications. We're trapped on our island. We can see other islands on the horizon, but the ocean between is simply too wide to cross. We're cosmologically isolated, able to observe, but never to visit, forever looking out at a universe we'll never touch. But there's another dimension to this isolation that's even more unsettling. The temporal dimension. When you look at Andromeda tonight, you're not seeing it as it exists now. You're seeing it as it was 2.5 million years ago. The light entering your eye left those distant stars when Homo habilis was chipping stone tools in East Africa, when our ancestors had brains 1/3 the size of ours, when the concept of humanity didn't exist yet because humans didn't exist. The Andromeda you observe is a ghost, a memory frozen in photons. Everything could have changed there since that light departed. Stars have been born and died. Planets have formed and perhaps been destroyed. If intelligent civilizations exist in Andromeda, entire empires could have risen, flourished for millennia, and collapsed into dust, all without us having any knowledge of it for another 2.5 million years. This creates a peculiar kind of cosmic loneliness. We can see Andromeda, but we can never know its present. We're forever locked into observing its past, receiving information on a delay longer than the entire evolutionary history of our species. And it gets stranger when you consider communication. Imagine we detected a radio signal from Andromeda tomorrow, an unmistakable pattern of pulses that could only be artificial, a message from an alien civilization. The excitement would be unprecedented. First contact, proof we're not alone, evidence of intelligence beyond Earth. But that message would be 2.5 million years old. The civilization that sent it existed when our ancestors were barely recognizable as hominids. By the time their message reaches us, they could be long extinct. Their entire species could have evolved, thrived, declined, and disappeared while their greeting was in transit. If we responded immediately, our reply wouldn't arrive for another 2.5 million years. Round-trip communication time, 5 million years. longer than the entire existence of genus Homo, longer than most mammalian species survive before going extinct or evolving into something else. You can't have a conversation across such distances. You can't exchange ideas or build relationships. The gulf of time is as insurmountable as the gulf of space. Even moving at light speed, information takes so long to travel that any exchange becomes meaningless. This is what physicists mean when they talk about cosmic horizons. Not just the edge of what we can see, but the boundary of what we can ever interact with. Andromeda exists beyond our causal horizon in any practical sense. We can observe it, but we can't affect it. We can receive information from it, but only ancient information. We can send signals toward it, but they'll arrive in an incomprehensibly distant future. The distance doesn't just separate us spatially, it separates us temporally, creates an unbridgeable gap in time as well as space. Now here's where the numbers become truly cruel. Andromeda is approaching us. Unlike most galaxies, which are receding due to cosmic expansion, Andromeda is moving toward the Milky Way at roughly 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide. Collision might be the wrong word. Galaxies are mostly empty space. When Andromeda and the Milky Way merge, very few stars will actually hit each other. The stars are so far apart that they'll mostly pass through like two clouds of gnats interpenetrating. The collision will be gravitational, not physical. The two galaxies will distort each other, triggering massive bursts of star formation, flinging some stars into intergalactic space, and eventually settling into a new configuration, an elliptical galaxy that astronomers have already nicknamed Milkomeda. But here's what's darkly funny about this. We're doomed to merge with Andromeda, but we still can't get there. The galaxy is approaching at 110 kilometers per second. Sounds fast, but at that speed, it would still take 21 billion years to cross the current distance. The collision only happens in 4.5 billion years because both galaxies are moving and the space between them is finite and shrinking. But if you wanted to travel from the Milky Way to Andromeda right now, you couldn't just wait for Andromeda to come to you. You'd arrive at the collision zone, but you wouldn't arrive at Andromeda as it exists today. You'd arrive at Andromeda in the future. The stars and planets you might want to visit would have already passed you by, scattered into new orbits by the gravitational chaos of the merger. The distances involved create paradoxes like this. Even when two objects are moving toward each other, even when they're destined to collide, the space between them remains vast enough that crossing it takes longer than the collision itself takes to occur. And remember, Andromeda is the closest large galaxy. It's our nearest galactic neighbor, the one right next door in cosmic terms. If we can't reach Andromeda, we certainly can't reach anything farther. The Triangulum Galaxy, third largest in our local group, sits about 3 million light-years away. The distances only grow from there. Centaurus A, 13 million light-years. The Virgo cluster, 65 million light-years. The Coma cluster, 320 million light-years. Each step outward multiplies the impossibility. The timescales expand beyond comprehension. The energy requirements grow beyond any conceivable capacity. The technological challenges compound until they become not just impractical but physically impossible, given the laws of nature as we understand them. And those are still nearby structures in cosmic terms. The observable universe extends 46.5 billion light-years in every direction. There are galaxies so distant, we see them as they were when the universe was less than 1 billion years old. Galaxies whose light has been traveling toward us for over 13 billion years. Those galaxies are receding from us faster than light, not because they're moving through space faster than light, which would violate relativity, but because the space between us and them is expanding faster than light can cross it. We can see those galaxies, but we can never reach them, ever, under any circumstances. Even if we could travel at light speed, we'd never catch up because they're receding faster than we're approaching. The expansion of space itself guarantees they remain forever beyond our grasp. Andromeda, at least, isn't receding. It's approaching. We share a gravitational fate, but that doesn't make it reachable. The distance is still too vast, and the laws of physics are still too restrictive. You might think this is depressing, a cosmic prison sentence, trapped in our local galactic neighborhood, able to see, but never to visit the broader universe. But there's another way to look at it. The fact that we can see Andromeda at all is extraordinary. The photons making that journey, crossing 2.5 million light-years of space, surviving the journey unchanged, arriving at your retina with enough energy to trigger the chemical reactions that create vision. That's miraculous. Those photons left Andromeda before humans existed, before Homo erectus, before Homo habilis. They traveled through space while our ancestors evolved from ape-like creatures into upright walkers, into tool users, into language speakers, into storytellers and philosophers and scientists. The light from Andromeda is older than our species. It's older than our genus. It's older than most of our evolutionary lineage, and yet it reaches us, carries information across impossible distances, allows us to see structure in the galaxy, to count its stars, to measure its motion, to understand its composition. We can't go there, but the light comes to us, brings Andromeda to our eyes every clear night, connects us across the void in the only way the universe allows, through the messenger of light. The distance to Andromeda is terrifying because it reveals the scale of our cosmic isolation. But it's also humbling because it shows how much we can learn despite that isolation, how far our observations can reach even when our bodies cannot. Every photon from Andromeda is a gift, a packet of information that traveled farther than we ever will, that crossed distances we can barely imagine, that brings us knowledge of a galaxy we'll never touch. The distance is insurmountable, but the light crosses it anyway. And in that crossing, in that patient journey of photons across millions of years and trillions of miles, the universe reveals itself to us, shows us what exists beyond our reach, proves that isolation doesn't mean ignorance. We're trapped on our island, yes, but we can see other islands. We can study them. We can understand them. We can map their shores and count their inhabitants and measure their motion through space. We can't visit Andromeda, but we can know it. And perhaps that's enough. Those photons carry more than just light. They carry a complete record of Andromeda's structure, composition and motion. Every wavelength encodes information. Every spectrum reveals chemical signatures. The ancient light becomes a time capsule, preserving knowledge from an era before our species existed. What have we learned from these patient messengers? Start with the basics. Andromeda is enormous. Its diameter stretches 220,000 light-years, more than double the Milky Way's span. The galaxy contains approximately 1 trillion stars, a number so large it defies visualization. 1 trillion individual suns, each potentially hosting planets, moons, asteroid belts. The Milky Way holds between 200 and 400 billion stars. Andromeda has at least twice that many, possibly 5 times more. The mass calculation is equally staggering. Andromeda weighs in at 1,230 billion solar masses. That's 1,230 billion times the mass of our Sun. The gravitational influence of that much matter dominates the local cosmic neighborhood, pulling smaller galaxies into orbit, warping space around it, commanding the gravitational dance of the local group. But here's where it gets interesting. For decades, astronomers classified Andromeda as a regular spiral galaxy. The visible light images showed elegant spiral arms, a bright central bulge, the classic structure we associate with galaxies like our own. Then, infrared observations changed everything. The Spitzer Space Telescope, observing in wavelengths invisible to human eyes, revealed something unexpected. Andromeda isn't a simple spiral. It's a barred spiral galaxy, just like the Milky Way. A massive bar of stars cuts across its center, oriented 55 degrees from the main disk. This bar was hidden in visible light, obscured by dust and the galaxy's angle relative to Earth. Only infrared could penetrate the veil. Why does this matter? Because barred spirals have different dynamics than regular spirals. The bar funnels gas toward the galactic center, feeding star formation and potentially feeding the supermassive black hole lurking there. The discovery meant revising our understanding of Andromeda's evolution and structure. The galaxy's internal architecture reveals even more complexity. Gas and dust don't distribute evenly. They organize into overlapping rings, like ripples frozen in space. One ring dominates, a structure at 32,000 light-years from the core. Astronomers call it the Ring of Fire, though that name is somewhat misleading. It's not literally on fire. It's cold dust, invisible in optical wavelengths, but it's where most star formation happens. This ring contains the raw material for stellar birth. Massive clouds of hydrogen and helium collapse under their own gravity, heating until fusion ignites, birthing new stars. The ring glows in infrared, revealing thousands of stellar nurseries hidden from visible light. Every year, this region produces roughly 1 new star. That might not sound like much, but over millions of years, it adds up. Hubble Space Telescope observations have resolved individual stars within Andromeda. Think about that for a moment. We're talking about a galaxy 2.5 million light-years away, and we can see individual stars. Not as points of light, we're not getting close-up images of stellar surfaces, but as discrete objects separated from their neighbors. Hubble's mosaic of Andromeda, assembled from 7,398 separate exposures across 411 telescope pointings, reveals over 100 million individual stars in a 61,000 light-year stretch of the galaxy's disk. The observations show blue supergiants, red giants, variable stars whose brightness changes over time. We can measure their temperatures, estimate their masses, track their motion. Ancient photons carry all this information across the void, delivering detailed reports on stars that existed long before humans walked upright. In 2005, astronomers discovered something completely new, a type of star cluster that shouldn't exist according to existing models. These clusters contain hundreds of thousands of stars, similar to globular clusters, but they're fundamentally different. They span several hundred light-years across, massive compared to typical globular clusters. and they're hundreds of times less dense. The stars within them are separated by vast distances. Nobody expected to find these objects. They don't fit neatly into our classification schemes. Are they young clusters that haven't collapsed yet? Are they old clusters that have expanded over time? Are they the remnants of disrupted dwarf galaxies? The photons from Andromeda revealed their existence, but the explanation remains elusive. Now consider the center. Every major galaxy harbors a supermassive black hole at its core. Andromeda is no exception. The monster at its heart weighs approximately 100 million solar masses. That's at least 25 times more massive than Sagittarius A star, the supermassive black hole at the Milky Way's center. 100 million suns compressed into a region smaller than our solar system. The gravitational field is so intense that nothing within the event horizon can escape. Not matter, not energy, not even light itself. The black hole's gravity dominates the galaxy's central region, dictating the motion of millions of nearby stars. Strangely, this massive black hole is quiet. Despite its enormous mass, it emits very little radiation. It's not actively feeding on large amounts of matter. Most supermassive black holes in galaxy centers are either actively consuming material, producing brilliant quasar-like emissions, or relatively dormant. Andromeda's black hole falls into the dormant category, along with our own galactic center. But dormant doesn't mean inactive. The black hole still feeds, just slowly. Long filaments of dust and gas spiral inward, approaching gradually, like water circling a drain. The material heats as it accelerates, emitting X-rays and other radiation. Occasionally, the black hole flares, brief bursts of activity when larger chunks of matter fall in. These flares reveal the black hole's presence, even when we can't see it directly. The photons from these flares began their journey 2.5 million years ago. When that radiation left Andromeda, the black hole was consuming matter that has long since crossed the event horizon. The flare we observe today is ancient history. The black hole's current state remains unknown, hidden behind the light travel delay. What else do the photons tell us? Motion. The light from Andromeda is blue shifted. This is unusual. Most distant galaxies show redshift, their light stretched to longer wavelengths by the expansion of space. But Andromeda approaches at roughly 110 kilometers per second. The motion compresses the light waves slightly, shifting them toward the blue end of the spectrum. This blue shift revealed something profound. Andromeda isn't just drifting randomly through space. It's on a collision course with the Milky Way. The two galaxies are falling toward each other, pulled together by mutual gravitational attraction. In approximately 4.5 billion years, they'll merge. Actually, recent calculations have complicated this prediction. When astronomers factor in the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, the certainty decreases. New simulations suggest only a 50% chance of direct collision within the next 10 billion years. Some models predict a near miss instead, a close encounter that distorts both galaxies without full merger. Other models suggest the collision might be delayed or altered by the complex gravitational dynamics of the local group. But even a collision isn't quite what it sounds like. Galaxies are mostly empty space. Stars are separated by distances millions of times their own diameter. When Andromeda and the Milky Way merge, individual stars almost certainly won't collide. They'll pass by each other like ships in the night. The galaxies will interpenetrate. their stars mixing but rarely touching. What will collide are the gas clouds. When massive clouds of interstellar hydrogen slam together at hundreds of kilometers per second, they compress. Compression triggers star formation. The collision will ignite a starburst, a period of intense stellar birth as gas clouds throughout both galaxies collapse and ignite. The night sky will fill with brilliant blue supergiants and massive stellar nurseries. This is billions of years away. Earth will likely be uninhabitable long before then. The sun will have expanded, boiling away our oceans, rendering the planet sterile. But if any future observers witness the merger from this region of space, they'll see something spectacular. None of this would be known without those ancient photons. Every detail about Andromeda's structure, motion, and composition comes from analyzing light that crossed 2.5 million light-years of space. We can't send probes. We can't collect physical samples. We can only study the electromagnetic radiation that reaches us. And we've gotten remarkably good at extracting information from that radiation. Spectroscopy breaks light into component wavelengths, revealing which elements are present in distant stars. Different elements absorb and emit specific wavelengths. By analyzing absorption lines in stellar spectra, we can determine chemical composition without ever touching the star. Photometry measures brightness variations over time. Variable stars pulse, eclipse, or flare in predictable patterns. By monitoring these changes, we can determine stellar properties, binary star systems, even the presence of planets transiting in front of distant suns. Astrometry tracks positional changes across years or decades. Stars move relative to each other. By measuring these tiny motions, we can map Andromeda's rotation, calculate its mass distribution, understand its gravitational structure, all from positional shifts measured in milliarc seconds, angles smaller than a single human hair viewed from across a football field. The 2006 Spitzer observations that revealed Andromeda's trillion stars relied on infrared photometry. The telescope counted individual stars by their infrared emissions, cutting through dust that obscures visible light. Previous estimates had suggested 200 to 400 billion stars. Spitzer's infrared census more than doubled that number. Hubble's detailed imaging revealed another surprise. Andromeda's disk contains a population of metal-rich stars. In astronomical terms, metals means anything heavier than hydrogen and helium. These elements are forged in stellar cores and scattered by supernovas. Their presence indicates that Andromeda has experienced significant star formation and stellar death over its history. The metallicity variations across the galaxy tell a story of chemical evolution. The central regions are metal-rich, enriched by billions of years of stellar recycling. The outer regions are metal-poor, containing more pristine material from the galaxy's early formation. This gradient reveals how Andromeda assembled itself over cosmic time. We've even detected individual Cepheid variables in Andromeda. These pulsating stars vary in brightness with periods ranging from days to months. The period correlates directly with the star's intrinsic luminosity. By measuring how bright a Cepheid appears and comparing it to how bright it should be based on its pulsation period, we can calculate its distance with remarkable precision. This is how Edwin Hubble determined Andromeda's distance in 1925. He identified Cepheids, measured their periods, calculated their distances, and proved that Andromeda lay far beyond the Milky Way's boundaries. The galaxy wasn't a nearby nebula, it was an entirely separate island universe. That discovery revolutionized astronomy. Before 1925, many astronomers believed the Milky Way constituted the entire universe. Everything visible was assumed to be part of our galaxy. Hubble's observations shattered that assumption. The universe suddenly expanded by orders of magnitude. Instead of one galaxy, we lived in a cosmos containing billions, all from studying variable stars in Andromeda, from measuring the brightness fluctuations of individual pulsating suns 2.5 million light-years away, from analyzing photons that began their journey before humans existed. The galaxy continues revealing secrets. Modern telescopes detect gravitational lensing around Andromeda, space warped by the galaxy's mass. This lensing provides independent confirmation of the galaxy's total mass, including dark matter. Observations suggest Andromeda's dark matter halo extends far beyond the visible disk, encompassing a region several times larger than what we see in photographs. Radio observations have mapped Andromeda's magnetic field. The galaxy generates a large-scale magnetic structure through dynamo action, the same process that creates Earth's magnetic field, but on a galactic scale. These magnetic fields influence star formation, guide cosmic rays, and shape the distribution of interstellar gas. X-ray observations reveal hundreds of X-ray sources throughout the galaxy. Many are binary star systems, where a compact object, a neutron star or black hole, accretes matter from a companion star. The infalling material heats to millions of degrees, emitting X-rays. Each source represents a stellar system in a dramatic phase of evolution. Every wavelength reveals different aspects of the galaxy. Visible light shows stars. Infrared penetrates dust. Radio maps gas and magnetic fields. X-rays highlight high-energy processes. Ultraviolet traces hot young stars. We've observed Andromeda across the entire electromagnetic spectrum, from radio waves to gamma rays. And we're not finished. Future telescopes will probe deeper, resolve finer details, detect fainter signals. Each new observation answers old questions and raises new ones. The photons keep arriving, patient messengers carrying information across the cosmic void. That's what makes the distance simultaneously terrifying and magnificent. We can't go there, but the light brings Andromeda to us. The light traveling from Andromeda carries something else: evidence of motion. When astronomers analyze the spectrum of Andromeda's light, they notice something unusual. The spectral lines are shifted toward the blue end of the spectrum. This blue shift reveals that Andromeda is moving toward us at approximately 110 kilometers per second. While the universe expands and most galaxies recede from us, their light stretch toward red wavelengths. Andromeda approaches. Gravity overcomes cosmic expansion at this local scale. The gravitational attraction between the Milky Way and Andromeda pulls them together despite the universe's overall expansion. This approach sets up one of the most dramatic events in the distant future: a galactic collision. In approximately 4.5 billion years, though recent calculations suggest the timeline and probability are more uncertain, these two massive galaxies will begin merging. The word collision evokes violent destruction, but galactic mergers unfold differently than we might imagine. Galaxies are mostly empty space. The distances between stars are vast compared to the stars themselves. When galaxies collide, individual stars rarely impact each other. Instead, they pass through the merging structure like two swarms of bees flying through each other. But gravity reshapes everything. As the galaxies interpenetrate, Gravitational forces distort their elegant spiral structures. Stars get flung into new orbits. Some accelerate, some slow down. The orderly rotation of each galaxy transforms into chaotic motion. Computer simulations show the galaxies making several close passes, their shapes warping and stretching with each encounter. Tidal tails of stars stream out into intergalactic space. The supermassive black holes at each galaxy's center spiral inward, eventually merging into a single, even more massive black hole. The final product will be an elliptical galaxy, a smooth, featureless collection of stars with little gas and minimal star formation. Astronomers have already named this future galaxy Milkomeda, or Milkdromeda. The merger will fundamentally alter the night sky for any civilizations that exist at that time. The familiar constellations will have dispersed. The galactic disk will have transformed into a spherical distribution of stars. Earth's sun might be ejected into intergalactic space, or it might settle into a different orbit within the new galaxy. But that's 4.5 billion years away. Today, that distance, 2.5 million light-years, keeps the galaxies separate. The vastness preserves their individual identities. They approach, but the journey takes eons. This demonstrates another aspect of cosmic distances. They don't just separate objects in space, they separate events in time. The collision will happen, but the distance ensures it unfolds on timescales incomprehensible to human experience. Consider what this means for potential life in Andromeda. If civilizations exist there, they're as unreachable to us as we are to them. A radio signal sent today would arrive in 2.5 million years. If they responded immediately, we'd receive their reply in 5 million years. This makes any form of two-way communication impossible. By the time a conversation could complete one exchange, both civilizations might have risen, evolved, and disappeared. The distance creates not just spatial isolation, but temporal isolation. We're forever locked into our local cosmic neighborhood, able to observe distant galaxies, but never meaningfully interact with them. Some propose that advanced civilizations might overcome this barrier with technology we can't yet imagine. Warp drives that compress space in front of a spacecraft and expand it behind. Wormholes connecting distant points in space. Quantum entanglement enabling instantaneous communication. These concepts exist in theoretical physics, but they all face enormous obstacles. Warp drives require exotic matter with negative energy density, something we've never observed and aren't sure exists. Wormholes, if they can exist at all, would likely be microscopic and unstable. Quantum entanglement can't transmit information faster than light, despite the instantaneous correlation between entangled particles. The universe appears to enforce the speed of light limit strictly. Nothing we've discovered suggests a practical way around it. This means the distance to Andromeda might represent a permanent barrier. We can send our fastest spacecraft, and it would take billions of years to arrive. We can beam our most powerful signals, and they would take millions of years to reach their destination. The vastness doesn't just make travel difficult, it makes it functionally impossible given the laws of physics as we understand them. Yet this impossibility has a strange beauty. The distance preserves mystery. If we could easily reach Andromeda, it would become mundane, catalogued, fully explored. The separation maintains wonder. We can observe, we can study, we can imagine, but we cannot possess. Andromeda remains forever beyond our grasp, a cosmic neighbor we can see but never visit. This raises philosophical questions about our place in the universe. Are we meant to remain confined to our local region? The observable universe contains approximately 2 trillion galaxies. Most lie far beyond Andromeda. The farthest galaxies we can observe exist at distances of over 13 billion light-years, seen as they were when the universe was young. We observe them, but we're even more thoroughly isolated from them. The expansion of space carries them away faster than light could ever reach them. We see their ancient light, but they're already beyond any possible contact. Perhaps this isolation shapes the nature of intelligence in the universe. If civilizations can only influence their local cosmic neighborhood, then the universe fragments into countless independent regions. Each develops in isolation. Different solutions to the problems of existence emerge. The universe becomes a vast experiment with billions of independent trials, each exploring different possibilities without interference from the others. Or perhaps we're thinking too narrowly. Maybe advanced civilizations discover principles we haven't yet understood, physics beyond our current theories, technologies that seem impossible with our limited knowledge. After all, someone from the 19th century couldn't have imagined nuclear power, quantum computers, or genetic engineering. Our understanding of what's possible is limited by our current knowledge. Future discoveries might reveal options we can't currently conceive, but we can only work with what we know. And what we know says that Andromeda, at 2.5 million light-years away, remains fundamentally unreachable. The fastest spacecraft we've ever built would take billions of years to get there. The fastest signal we could send would take millions of years. The distance defeats any practical attempt at contact or travel. This makes the fact that we can observe Andromeda at all feel miraculous. Those photons crossing the void, that ancient light reaching our telescopes. We can't go there, but the galaxy comes to us through electromagnetic radiation. Every photon carries information. Wavelength reveals composition. Intensity indicates brightness. Spectral lines show motion. Patterns disclose structure. From 2.5 million light-years away, we can determine what elements exist in Andromeda's stars, how fast the galaxy rotates, where star formation occurs, what happened in its past. This observational power represents humanity's primary tool for understanding the distant universe. We might never physically travel to Andromeda, but we can study it in remarkable detail. Telescopes serve as time machines and space probes simultaneously. They let us see distant objects as they were when their light began its journey. They let us analyze those objects' properties without leaving Earth. Every improvement in telescope technology reveals more details, answers more questions, deepens our understanding. The James Webb Space Telescope now provides infrared images of unprecedented clarity. It can resolve individual star-forming regions in Andromeda. It can detect the faint glow of the oldest stars. It can measure the galaxy's temperature, composition, and structure with precision previous generations couldn't imagine. Future telescopes will do even better. Larger mirrors will gather more light. Advanced detectors will capture fainter signals. New wavelengths will reveal hidden phenomena. Each improvement brings Andromeda closer in an informational sense. Even though the physical distance remains unchanged, we learn more. We see deeper. We understand better. The light keeps arriving, and we keep extracting meaning from it. This process will continue as long as humans build telescopes and ask questions about the cosmos. But there's a limit to observation too. We can only observe what light reveals. Dark matter, which comprises most of Andromeda's mass, doesn't emit light. We detect it through gravitational effects, how it influences visible matter, how it bends light from background objects. But we can't see it directly. We can't determine its exact distribution or understand its fundamental nature through observation alone. The distance makes direct experiments impossible. Similarly, we can't know what's happening in Andromeda right now. We see the galaxy as it was 2.5 million years ago. Anything could have changed since then. Stars could have exploded. New structures could have formed. Civilizations could have arisen or vanished. We won't know for another 2.5 million years when the light from those events reaches us. The distance creates a permanent information delay. We're always seeing the past, never the present. This temporal displacement affects everything we observe in the universe. When we look at the sun, we see it as it was 8 minutes ago. When we observe the nearest star system, Alpha Centauri, we see it as it was 4.37 years ago. When we study Andromeda, we see it as it was 2.5 million years ago. When we observe the most distant galaxies, we see them as they were over 13 billion years ago, when the universe was young and very different from today. Astronomy is inherently historical. We study the past because light takes time to travel. The farther we look, the further back we see. Andromeda shows us the galaxy's state during Earth's Pleistocene epoch. Distant galaxies show us the universe's state shortly after the Big Bang. We can never observe the present state of distant objects. The speed of light enforces this limitation absolutely. Yet this limitation provides advantages. By observing objects at different distances, we observe different cosmic eras. Nearby galaxies show us the universe's recent history. Distant galaxies show us ancient history. By comparing observations across different distances, we can trace cosmic evolution. We can watch how galaxies change over time, how star formation rates evolve, how chemical composition builds up through successive generations of stars. Andromeda sits at an ideal distance for certain studies, close enough that we can resolve individual stars and structures, far enough that we see the galaxy as an integrated whole, not so distant that redshift and dimming make observations difficult, not so nearby that it fills our entire field of view. The 2.5 million light-year distance provides a sweet spot for galactic astronomy. This distance also means Andromeda appears relatively bright despite being far away. Its apparent magnitude of 3.4 makes it visible to the naked eye under dark skies. You can see it without any equipment, just your eyes and a moonless night. That accessibility has allowed humans to observe Andromeda for over 1,000 years, long before we understood what galaxies were or how far away they existed. The Persian astronomer Abd al-Rahman al-Sufi described it in 964 CE as a small cloud. He didn't know it was a galaxy. He didn't know it contained 1 trillion stars. He didn't know it lay millions of light years away. He simply recorded what he saw, a fuzzy patch of light that didn't quite look like a star. That observation, preserved in his Book of Fixed Stars, represents the first written record of Andromeda. Later observers added details. With telescopes, they could resolve more structure. They could see that it wasn't just a cloud, but an extended object with a bright center and fainter surroundings. But they still debated what it was. Some thought it was a nebula within our galaxy. Others suspected it might be something more distant and exotic. The debate continued for centuries. Edwin Hubble's 1925 observations finally settled the question. By identifying Cepheid variable stars in Andromeda and measuring their distances, he proved the galaxy lay far beyond the Milky Way's boundaries. The universe suddenly expanded. What had been considered the entirety of existence, our galaxy, became just one among countless others. Andromeda was an island universe, a separate galaxy comparable to our own. That revelation fundamentally changed humanity's cosmic perspective. We weren't the center of everything. We weren't even in a special galaxy. We occupied one ordinary galaxy among billions. The universe was vastly larger than anyone had imagined, and Andromeda, that fuzzy patch visible to the naked eye, was an entire galaxy of stars, sitting 2.5 million light-years away. That discovery came from observing pulsating stars, Cepheid variables, whose brightness changes in predictable rhythms. Henrietta Swan Leavitt had discovered something remarkable about these cosmic metronomes. The longer their pulsation period, the brighter they actually were. This relationship meant astronomers could measure a Cepheid's true brightness by timing its pulses, then compare that to how bright it appeared from Earth. The difference told them the distance. Hubble found Cepheids in Andromeda. He timed their pulses. He calculated their distances. The numbers were staggering. Andromeda lay nearly 1 million light-years away, far beyond what anyone had imagined possible. Later refinements pushed that figure to 2.5 million light-years. But the revelation remained the same. We weren't alone in the cosmos. We weren't even in a unique galaxy. We occupied one island among countless others, scattered through an ocean of space, so vast it defied comprehension. What changed that night wasn't just astronomy, it was philosophy. Humanity's cosmic address expanded from a single building to an entire city of galaxies. And Andromeda, visible to anyone with clear skies and patience, represented the nearest neighbor in that cosmic metropolis. But here's what makes Andromeda truly extraordinary among distant objects. It's not receding from us. Most galaxies are rushing away, carried by the expansion of space itself. The farther they are, the faster they recede. This cosmic expansion, discovered by Hubble through his observations of galaxy redshifts, reveals a universe that's been growing since the Big Bang. Every distant galaxy shows light stretch toward redder wavelengths, a Doppler shift caused by their motion away from us. Andromeda shows the opposite. Its light is blue shifted. The galaxy is approaching at roughly 110 kilometers per second. Not because space is contracting, but because Andromeda and the Milky Way are gravitationally bound. We're falling toward each other, slowly but inevitably. In approximately 4.5 billion years, give or take, these two galaxies will collide. Calling it a collision doesn't quite capture what will happen. Galaxies aren't solid objects. They're mostly empty space with stars scattered through vast volumes. When Andromeda and the Milky Way merge, individual stars will almost certainly not hit each other. The distances between stars are too enormous. Imagine two swarms of fireflies passing through each other. That's closer to reality than two rocks smashing together. But the galaxy's gas clouds will collide. Those collisions will compress gas, triggering enormous waves of star formation. The night sky will blaze with new stellar nurseries. Massive stars will live fast and die young, exploding as supernovae. The merger will be violent and beautiful, a cosmic fireworks display lasting millions of years. Recent research has questioned whether this collision is certain. Simulations incorporating data from the Gaia spacecraft and Hubble telescope suggest the odds might be lower than previously thought. Some models show only a 50% chance of a head-on collision within the next 10 billion years. When you factor in gravitational influences from the Large Magellanic Cloud and Triangulum Galaxy, the probability of a direct hit in the next 4 to 5 billion years drops to just 2%. Even if the galaxies miss on their first pass, they'll eventually merge. Gravity doesn't give up. The galaxies will swing past each other, then fall back together, dancing a slow gravitational waltz that could take billions of years before they finally settle into a single elliptical galaxy. Some astronomers have already named this future merger Milkomeda. But we're getting ahead of ourselves. Right now, Andromeda sits 2.5 million light-years away, and that distance creates something profound, a communication barrier that transcends technology. Imagine discovering intelligent life in Andromeda. Your telescope reveals unmistakable signs of civilization, artificial structures, energy signatures, deliberate patterns in electromagnetic radiation. You've found aliens. You send a message, traveling at light speed, the fastest possible transmission. That message arrives in 2.5 million years. If they receive it and immediately respond, their reply arrives 2.5 million years after that. Total round-trip time, 5 million years. 5 million years ago, Earth's climate was warmer. Early hominids were just beginning to diverge from other apes. No humans existed. No language, no writing, no civilization. The species that sent your message wouldn't exist when the reply arrived. Neither would their descendants' descendants through countless generations. This isn't a technical limitation. We can't solve it with better transmitters or more sensitive receivers. The speed of light creates an absolute barrier to real-time communication across such distances. Any conversation with Andromeda would span timescales longer than human history. Questions would outlive empires. Answers would arrive to civilizations that had forgotten the questions. This temporal isolation affects more than communication. It shapes what we can know about Andromeda itself. The galaxy we observe tonight existed 2.5 million years ago, during Earth's Pleistocene epoch, when Homo habilis was using primitive stone tools. When mastodons roamed North America, modern humans, Homo sapiens, wouldn't appear for another 2.2 million years. What's Andromeda actually doing right now? We can't know. We won't know for another 2.5 million years. Stars could have been born and died since the light we're seeing left. Planetary systems could have formed. Civilizations could have risen, flourished, and vanished. Supernova explosions could have occurred. The supermassive black hole at Andromeda's center could have devoured entire star systems. All of that remains invisible to us, hidden behind the light-speed delay that separates present reality from observable history. This look-back time effect pervades astronomy. Every observation is archaeological. The sun appears as it was 8 minutes ago. The nearest star beyond the sun shows us its state from over 4 years past. Andromeda reveals ancient history, and the most distant galaxies we can observe, billions of light years away, show us the universe when it was young, when the first stars were forming, when cosmic structures were just beginning to take shape. We're looking into the past every time we look up. Distance and time become interchangeable. Astronomers speak of objects being far away and long ago, as if they're the same thing, because they are. Light takes time to travel. The farther away something is, the further back we see. This creates a strange asymmetry in our knowledge. We can observe the distant past, but never the distant present. We can see how galaxies looked billions of years ago, but not how they look now. The present state of distant objects remains forever beyond our reach, hidden behind the cosmic horizon created by the finite speed of light. Andromeda exists in that twilight zone, close enough that we can study it in exquisite detail, far enough that we're always seeing its past. The Hubble Space Telescope has captured stunning images of Andromeda, assembled from 7,398 exposures across 411 pointing positions. The resulting mosaic reveals over 100 million individual stars and thousands of star clusters in a 61,000 light-year stretch of the galaxy's disk. Those stars existed 2.5 million years ago. Some might be gone now. Others might have formed since. We're seeing a historical record, not a live feed. This temporal displacement affects how we study galactic evolution. We can't watch a single galaxy change over time. No human lifetime, no civilization's lifetime, spans enough time to observe significant galactic evolution in real time. Instead, we observe different galaxies at different distances, seeing them at different cosmic ages, then piece together how galaxies evolve by comparing snapshots from different eras. Nearby galaxies like Andromeda show us recent galactic history. Moderate distance galaxies show us intermediate stages. The most distant galaxies show us ancient primitive forms. By comparing these observations, we trace how galaxies change from youth to maturity, even though we can never watch a single galaxy actually make that journey. Andromeda serves as a critical reference point in this cosmic timeline. It's close enough that we can resolve individual stars and structures with current telescopes, far enough that we see it as an integrated system rather than being overwhelmed by proximity. Not so distant that redshift and dimming complicate observations. Not so nearby that it dominates our entire sky. The 2.5 million light-year distance provides an ideal vantage point for studying galactic structure and evolution. We can observe Andromeda's spiral arms, its central bulge, its satellite dwarf galaxies, its globular clusters, its star-forming regions. We can measure its rotation, its mass distribution, its chemical composition. Infrared observations from the Spitzer Space Telescope revealed something unexpected. Andromeda isn't just a spiral galaxy, it's a barred spiral, like the Milky Way. Visible light images don't show the bar clearly, but infrared penetrates dust to reveal the galaxy's underlying structure. The bar's major axis sits oriented 55 degrees counterclockwise from the disk's major axis, creating a twisted, complex geometry. The galaxy's gas and dust form overlapping rings. One particularly prominent ring sits about 32,000 light-years from the core. Astronomers nicknamed it the Ring of Fire because most of Andromeda's star formation concentrates there. Visible light images miss it entirely. It's composed primarily of cold dust. But infrared observations show it blazing with stellar nurseries where new suns are being born. Andromeda also contains stellar structures that don't fit known categories. In 2005, astronomers discovered unusual star clusters containing hundreds of thousands of stars. They resemble globular clusters but with crucial differences. They're much larger, several hundred light-years across. They're hundreds of times less dense, with much greater distances between individual stars. Nobody knows how they formed or why they exist only in Andromeda and a few other galaxies. These discoveries highlight how much we still don't understand about our nearest galactic neighbor. Despite over a century of intensive study, Andromeda keeps revealing surprises. Each new observation, each improved instrument, uncovers structures and phenomena that challenge our theories about how galaxies work. At Andromeda's heart lurks something particularly mysterious. A supermassive black hole containing roughly 100 million solar masses, at least 25 times more massive than Sagittarius A star, the supermassive black hole at the Milky Way's center. Despite this enormous mass, Andromeda's central black hole is surprisingly quiet. It emits very little radiation, suggesting it's not actively feeding on surrounding material. Most supermassive black holes at galaxy centers are either dormant like this, or actively accreting matter and blazing with radiation. Andromeda's falls into the dormant category, sipping material through long filaments of dust and gas that spiral inward gradually, like water circling a drain. This black hole represents a gravitational well so deep that nothing can escape once it crosses the event horizon. Not matter, not light, not information. Everything that falls in is lost to the external universe, locked behind a boundary from which there is no return. The event horizon sits at roughly 300 million kilometers, about twice the distance from Earth to the Sun. Inside that boundary, space itself is falling inward faster than light can travel outward. Time becomes space, space becomes time, and escape becomes literally impossible. We can observe matter spiraling toward that horizon. We can watch as it accelerates, heats up, emits X-rays from the tremendous friction and compression. But we can never see what happens inside. The event horizon is a one-way membrane. Information enters but never leaves. This informational barrier is absolute. It's not a technological limitation but a fundamental feature of space-time geometry. Black holes don't just trap matter and energy, they trap causality itself. Andromeda's supermassive black hole has been there for billions of years, slowly growing as it consumes gas, dust, and occasional stars. When the Milky Way and Andromeda eventually merge, their central black holes will spiral together and merge too, creating an even more massive gravitational monster. That merger will release gravitational waves, ripples in space-time itself, carrying energy equivalent to millions of suns. These waves will propagate outward at the speed of light, stretching and compressing space as they pass. By the time they reach Earth, assuming Earth still exists, they'll be detectable only by the most sensitive instruments, but that's billions of years away. Right now, Andromeda sits there, 2.5 million light-years distant, a trillion stars slowly orbiting a central void that warps space-time into impossible geometries. Surrounding that central void sits a trillion stars, each potentially hosting planets, moons, entire solar systems we'll never observe in detail. Some of those stars are nearly as old as the universe itself, ancient red giants that witnessed the galaxy's formation. Others are young, hot, blue stars born just millions of years ago from collapsing clouds of gas and dust. Somewhere in Andromeda, at this very moment, stars are being born. Gas clouds collapse under their own gravity, temperatures rise, nuclear fusion ignites. The same process that created our sun is happening there. 2.5 million light-years away, completely invisible to us because the light from those stellar births hasn't reached Earth yet. Somewhere else in Andromeda, stars are dying. Massive stars are exploding as supernovae, scattering heavy elements into space, seeding future generations of stars and planets with the raw materials for rocky worlds and possibly life. Other stars are quietly fading, swelling into red giants before shedding their outer layers and collapsing into white dwarfs. All of this is happening right now in Andromeda. We just can't see it yet. What we see when we look at Andromeda is the past, not a recent past, but a past so distant it predates modern humans. The photons reaching our eyes tonight left Andromeda when our ancestors were Homo habilis, primitive hominids using crude stone tools on the African savanna. Modern humans, Homo sapiens, wouldn't appear for another 2.2 million years after those photons began their journey. Agriculture, civilization, writing, everything we consider human history happened while those photons were crossing the void between galaxies. This temporal disconnect is one of the most philosophically unsettling aspects of cosmic distances. We're not just separated from Andromeda by space, but by time. We can never see Andromeda as it is now, only as it was. If an advanced civilization in Andromeda is observing Earth right now with impossibly powerful telescopes, they're not seeing us. They're seeing Earth 2.5 million years ago. They're watching a world where humans don't exist yet, where megafauna roam the continents, where the climate cycles through ice ages and warm periods with no awareness from any intelligent species. Imagine trying to communicate across this distance. You send a message today, a radio signal traveling at light speed. It arrives in Andromeda 2.5 million years from now. If they immediately respond, you receive their reply 5 million years after you sent your original message. That's not communication in any meaningful sense. It's cosmic message in a bottle, where the round-trip time exceeds the lifespan of civilizations, possibly of entire species. This fundamental barrier isn't technological. We can't overcome it with better engineering or more powerful transmitters. It's written into the structure of space-time itself. The speed of light isn't just fast, it's the maximum speed at which information can travel. And at cosmic distances, even that ultimate speed becomes painfully, impossibly slow. But perhaps the most unsettling aspect of Andromeda's distance isn't the physical gulf or the temporal disconnect. It's what that distance reveals about our place in the universe. We exist in a local group of galaxies, gravitationally bound together. Andromeda, the Milky Way, Triangulum, and about 50 smaller dwarf galaxies form a gravitational island in space. Beyond this island, other galaxies recede from us, carried away by the expansion of space itself. The local group spans about 10 million light-years. Andromeda sits at 2.5 million light-years, a significant fraction of our entire cosmic neighborhood. Beyond the local group lie other galaxy groups and clusters. The Virgo cluster contains over 1,500 galaxies and sits about 54 million light-years away. The Coma cluster, containing over 1,000 galaxies, is roughly 300 million light-years distant. These distances continue scaling upward. The observable universe extends 46.5 billion light-years in all directions, containing approximately 2 trillion galaxies. Within this vast cosmic arena, Andromeda is remarkably close. It's one of our nearest neighbors, close enough to see with the naked eye. close enough to study in detail with telescopes, yet it's still completely unreachable. Think about what this means. The closest major galaxy to us, visible as a faint smudge in our night sky, is so distant that we could never visit it with any remotely plausible technology. Not in our lifetimes, not in 1,000 lifetimes, not in 1,000,000 lifetimes. Even if we achieved the impossible and built spacecraft traveling at 10% light speed, a velocity that would require technological breakthroughs we can barely imagine, the journey would still take 25 million years. The crew that departed wouldn't just be separated from Earth by distance. They'd be separated by evolutionary time. By the time they arrived, they would have evolved into something else entirely, shaped by the unique pressures of life aboard a generation ship crossing intergalactic space. The human species itself might not exist anymore by then. 25 million years is a staggering span of biological time. For reference, the common ancestor we share with chimpanzees lived only 6 million years ago. So any civilization that successfully traveled to Andromeda would no longer be the civilization that launched the mission. The descendants arriving would be so changed, so adapted to their journey, that they'd be a different species carrying out a mission whose original purpose might be completely forgotten. This isn't science fiction speculation. This is the reality imposed by distance and the speed of light. Space doesn't just separate places, it separates possibilities. Perhaps that's the real terror of Andromeda's distance. Not that it's far away, but that it represents a fundamental limit to human experience. There are places in the universe we will never go, things we will never see directly, questions we will never answer. We're confined to our local group, and even within that cosmic neighborhood, most destinations remain impossibly distant. We're stuck on our pale blue dot, orbiting an ordinary star in an ordinary galaxy, able to observe the universe, but unable to explore most of it. This confinement isn't temporary. It's not something better technology will solve. It's built into the architecture of space-time itself. As the universe continues expanding, this isolation will only deepen. Galaxies beyond our local group are receding from us, carried by the expansion of space itself. Some are receding faster than light can travel, meaning we're seeing them now, but in the far future, their light will never reach us again. Eventually, billions of years from now, the observable universe will shrink. Distant galaxies will disappear beyond our cosmic horizon, their light stretched to infinite wavelengths by the expansion of space. If intelligent observers exist in that distant future, they'll look out at the night sky and see only the local group. The rest of the universe will have vanished beyond reach, leaving no evidence it ever existed. They'll be unable to discover the Big Bang, unable to measure cosmic expansion, unable to determine the universe's age or structure. They'll live in an island universe, surrounded by darkness, with no way to know about the larger cosmos beyond. We're lucky. We exist at a moment in cosmic history where we can still observe the distant universe. We can see galaxies billions of light years away, look back to when the universe was young, measure the expansion rate, calculate the age of the cosmos. But that observational window is temporary. Andromeda represents both what we can see and what we can never reach. When you look at Andromeda tonight, you're seeing a galaxy as it was 2.5 million years ago. You're observing the distant past of a place you'll never visit, witnessing stars that might not even exist anymore. That fuzzy patch of light in the autumn sky contains 1 trillion suns. a supermassive black hole, stellar nurseries and graveyards, possibly billions of planets, maybe even other civilizations looking back at us across the same unbridgeable gulf. All of it unreachable. All of it locked away behind a barrier of distance and time that no amount of human ingenuity can overcome. That's not a technological limitation. That's the structure of reality itself. Andromeda sits there, 2.5 million light-years away, close enough to see, too far to ever reach. A reminder that the universe is vast beyond comprehension, and we're confined to an infinitesimally small corner of it. The distance to Andromeda isn't just a number, it's a window into the fundamental architecture of the cosmos, revealing both the scale of the universe and the limits of what any intelligence, no matter how advanced, can ever experience. We observe the universe, we measure it, we try to understand it, but most of it will forever remain beyond our reach, separated from us by distances so vast they transcend human understanding. Andromeda is our neighbor, and will never meet. The 2.5 million light-year distance to Andromeda represents something more fundamental than mere separation. It's a window into the nature of the universe itself, revealing constraints written into the fabric of space-time that no technology can overcome. Every number we've examined points to the same conclusion. The fastest spacecraft humanity has built would take 3.9 billion years to arrive. A journey at 10% light speed, already wildly optimistic, still requires 25 million years. Even moving at light speed itself, an impossibility for anything with mass, the trip takes 2.5 million years. These aren't engineering challenges, they're physical impossibilities. The speed of light isn't arbitrary, it's the rate at which causality propagates through the universe, the maximum speed at which information can travel, the cosmic speed limit that ensures cause always precedes effect. Nothing with mass can reach it, much less exceed it, because the energy requirements approach infinity as you approach that velocity. This creates what physicists call light cones. Your future light cone contains everything you could potentially influence. Your past light cone contains everything that could have influenced you. Beyond those boundaries lies a realm you can observe but never affect. Andromeda exists outside your future light cone for any meaningful definition of you. By the time a signal from Earth reaches Andromeda, human civilization will have risen and fallen countless times. By the time a spacecraft arrives, the species that launched it will have evolved beyond recognition or gone extinct entirely. The temporal barrier compounds the spatial one. We're separated from Andromeda, not just by distance, but by time. The galaxy we observe tonight existed when Homo habilis chipped stone tools. The galaxy, as it exists right now, remains invisible to us, hidden behind the light speed delay that separates present reality from observable history. This look-back time effect pervades astronomy. Every observation is archaeological. We study the past because light takes time to travel. The farther we look, the deeper into history we peer. Andromeda shows us galactic structure from 2.5 million years ago. Distant galaxies reveal the universe when it was young. We're looking at a cosmos that no longer exists in the forms we observe. Communication across such distances becomes meaningless. Send a message to Andromeda today, and it arrives in 2.5 million years. If they immediately respond, you receive their reply 5 million years after your original transmission. No conversation can span such timeframes. No civilization lasts that long. No species remains unchanged through such epochs. The mathematics of cosmic distances reveals our isolation. We exist in a local group of gravitationally bound galaxies. Beyond this island, the expansion of space carries other galaxies away. Some recede faster than light can travel, not because they move through space at that speed, which would violate relativity, but because space itself expands between us. Eventually, billions of years from now, most galaxies will disappear beyond our cosmic horizon. Future observers will see only their local neighborhood. The rest of the universe will have vanished, leaving no evidence of the larger cosmos. They won't be able to discover the Big Bang or measure cosmic expansion. They'll live in darkness, surrounded by an apparently empty universe. We're fortunate. We exist at a cosmic moment when we can still observe the distant universe. We can see galaxies billions of light years away. We can look back to when stars first formed. We can measure how the universe has evolved. But observation isn't the same as access. We can see Andromeda, but we cannot go there. We can photograph it, analyze its spectrum, count its stars. We can determine its composition, measure its rotation, track its motion. We can resolve individual stellar nurseries and map dark matter halos. None of that changes the fundamental reality. Andromeda remains unreachable. This confinement isn't temporary. Better rockets won't solve it. Fusion drives, antimatter engines, even theoretical concepts like warp drives or wormholes all face insurmountable obstacles. The universe appears structured to enforce the speed of light limit absolutely. Every path around it requires exotic physics we've never observed and probably doesn't exist. Some find this depressing, a cosmic prison sentence, trapped in our local neighborhood, able to see but never visit the broader universe. But there's another perspective. The distance preserves mystery. If we could easily reach Andromeda, it would become mundane, catalogued, explored, understood. The separation maintains wonder. We can observe, study, imagine, but we cannot possess. Andromeda remains forever beyond our grasp. This might be how the universe structures intelligence. If civilizations can only influence their local regions, then the cosmos fragments into countless independent domains. Each develops in isolation. Different solutions to existence emerge. The universe becomes a vast experiment with billions of trials, each exploring different possibilities without interference. Perhaps advanced civilizations discover principles we haven't yet understood, physics beyond our current theories, technologies that seem impossible with limited knowledge. After all, someone from the 19th century couldn't have imagined nuclear power or quantum computers. Our understanding of what's possible is constrained by current knowledge. But we can only work with what we know. And what we know, says Andromeda, at 2.5 million light-years, remains fundamentally unreachable. Yet the fact we can observe it at all feels miraculous. Those photons crossing the void, that ancient light reaching our telescopes. We can't go there, but the galaxy comes to us through electromagnetic radiation. Every photon carries information. Wavelength reveals composition. Intensity indicates brightness. Spectral lines show motion. From 2.5 million light-years away, we determine what elements exist in Andromeda's stars, how fast the galaxy rotates, where star formation occurs. We resolve individual stars with Hubble. We map the supermassive black hole with X-ray observations. We trace dark matter through gravitational lensing. This observational power represents humanity's primary tool for understanding the distant universe. We might never physically travel to Andromeda, but we can study it in remarkable detail. Telescopes serve as time machines and space probes simultaneously. They show us distant objects as they were. They analyze those objects' properties without leaving Earth. Every improvement in telescope technology reveals more. The James Webb Space Telescope provides infrared images of unprecedented clarity. Future instruments will do better. Larger mirrors will gather more light. Advanced detectors will capture fainter signals. New wavelengths will reveal hidden phenomena. Each improvement brings Andromeda closer informationally, even though physical distance remains unchanged. We learn more, we see deeper, we understand better. The light keeps arriving, and we keep extracting meaning from it. But there's a limit to observation too. We can only see what light reveals. Dark matter doesn't emit radiation. We detect it through gravitational effects, but we can't observe it directly. The distance makes direct experiments impossible. We also can't know Andromeda's present state. We see the galaxy as it was 2.5 million years ago. Stars could have exploded since then. Civilizations could have risen or fallen. We won't know for another 2.5 million years when the light from those events reaches us. This temporal disconnect affects everything we observe. Astronomy is inherently historical. We study the past because light takes time to travel. The farther we look, the further back we see. We can never observe the present state of distant objects. The speed of light enforces this limitation absolutely. When you stand outside tonight and find Andromeda, you're seeing 1 trillion stars as they were when our ancestors were barely recognizable as human. That fuzzy patch of light contains entire solar systems, stellar nurseries, dying stars, possibly civilizations. All of it locked in the past. All of it unreachable. The distance to Andromeda isn't just far. It's a fundamental barrier written into reality itself. Space and time conspire to keep us isolated. We can observe the universe, but we cannot explore most of it. We're confined to our pale blue dot, orbiting an ordinary star in an ordinary galaxy. This confinement reveals something profound about existence. The universe is vast beyond comprehension, and we occupy an infinitesimally small corner. Most of what exists lies beyond our reach, separated by distances that transcend human understanding. Andromeda shows us both the scale of the cosmos and the limits of what any intelligence can experience. We observe it, we measure it, we try to understand it, but we'll never touch it, never visit its trillion stars, never explore its planets, never meet whatever civilizations might exist there. The galaxy sits 2.5 million light-years away, close enough to see, too far to ever reach. That's not a technological limitation. That's the structure of space-time itself. The universe has isolated us, able to observe but unable to visit, forever looking out at a cosmos we'll never touch. Every photon from Andromeda carries this message. The universe is larger than we can reach, older than we can comprehend, more mysterious than we can ever fully understand. And we're privileged to exist at a moment when we can still see it, study it, wonder at it, even knowing we'll never bridge the gulf that separates us from those distant shores. That's what makes the distance to Andromeda terrifying. Not its magnitude alone, but what it reveals about our place in the universe. We're observers, not explorers, witnesses to a cosmic drama we can never join. The distance isn't just a number, it's a boundary that defines the limits of human experience, showing us a universe we can see but never touch, understand but never possess, observe but never reach. Andromeda remains there, eternal and unreachable, a reminder that some things exist beyond our grasp, no matter how much we learn or how far we advance. The universe has drawn a line we cannot cross, and that line sits 2.5 million light-years away, separating us from a trillion stars we'll never visit, in a galaxy we'll only ever know through ancient light.